Assalamualaikum, everyone. Continue with the question 2C. Okay, is a state space model on translational mechanical system. Okay, so you are given this system in figure Q2C, where you have a two mass M1 and M2. You have about 1, 2, 3, 4 damper. Okay, 2 friction and 2 damper. And then you have 2 springs, K1 and K2, and 2 input, which is F1 and F2. Okay, and displacement is given by X1 and X2. Okay, so in this case, you have 2 displacement and 2 velocity, X1 dot and X2 dot. Okay, 2 force F1 and F2. Then you are required to establish the dynamic equation for X1 and X2. Okay, with the given state space variables X1, X2, X1 dot and X2 dot. So here, given state variables as Z1, Z2, Z3, and Z4, where Z1 is the displacement of X1, X2, X1 dot, and X2 dot. Okay, as given here. Okay, and then we find the derivative state variables. Okay, where Z1 dot is equal to X1 dot is equal to Z3, Z2 dot is equal to X2 dot equal to Z4, Z3 dot is equal to X1 double dot. This one we have to derive, and Z4 dot is equal to X2 double dot. So both of these we need to derive from the differential equation. But before we write the differential equation, we must draw the what do you call that, free body diagram. Or mass 1. Okay, so I draw the free body diagram M1, where you have a force over here F1, and then at the same time you have the M1 X1 double dot. Okay, K1 X1 FV3 X1 dot. Okay, then we have K2, which is X1 minus X2, and then FV1, which is X1 dot. Okay, so from here derive the differential equation. Okay, where m1 x1 double dot plus k1 x1 plus fv3 x1 dot plus k2 x1 minus x2 plus fv1 x1 dot equal to f1. Okay, so you rearrange the above equation. Okay, so we will get x1 dot, okay, which is equal to minus k1 plus k2 x1 plus k2 x2 minus x1 dot plus f1 divided by, okay, so here you already know that this x1 dot, x1 double dot is z3 dot, okay, x1 is z1, x2 z2, x1 dot is z3, and f1 is equal to u, the input. Okay. Then the next one is you draw the free body diagram for M2. Okay. F2 was M2, M2, X2 double dot, then K2 string, X2, and this one is the FV4, X2 dot, and the last one is FV2, which is X2 dot as well. Okay. So the differential equation, okay, given by M2 x2 double dot plus k2 2 minus x1 plus fv4 minus fv2 equal to f2. Okay. You rearrange the equation to get x2 double dot k2 divided by m2 minus k2 divided by m2 minus fv2 plus m2 plus f2 divided by m2. Okay, and from here, this is z4 dot. This one is z1 This one is Z2. This one is X2 dot Z4. And this one is a U2. Okay, second input. So the first input we label as U1. Second input we label as U2. So easy for us to reconstruct the state equations. But bear in mind that we have this one, okay, Z1 dot Z3, Z2 dot Z4. Okay, Z1 dot Z3, Z2 dot Z4. Okay, let us confirm. Okay, so now we have all the derivative state variables Z1 dot, Z2 dot, Z4 dot, and Z3 dot. So now we can simply construct the state equation. Okay. Okay, just do like this. Plus U1, U2. Okay. So the first state equation is 0, 0, 1, 0. Second one, 0, 0, 0, 1. Then the third state equation, K1, K2 over M1, K2 over M1, FV1 plus FV2, M1, 0, K2 over M2 minus K2 over M2, 0, minus FV2 plus FV4 divided by M2. Okay, so this is the state equation. Matrix A, matrix B is 0, 0, 0, 0, 1 over M1, 0, and 0, 1 over M. And the output of the system, okay, look here, what is the output? Okay. The output is the distance between two meshes is taken as the output. Distance between two meshes. Distance between two meshes. Okay. So we have two meshes, M1 and M2. So the difference, the distance is output y is equal to x1 minus x2. Okay. Simply indicate the distance between M1 and M2. Or we can write it as x2 minus x1. So both can be used. Okay. So in this case, usually we take x2 minus x1. So therefore, we have two state equation. It depends on how you take the difference between x1 and x2 and x2 x1. Okay. So y of t, the output is z1, z2, z3. Okay. So 1 minus 1. Or also can. Okay. So the output is defined as the absolute difference in position between two meshes. Both answer is correct. Question 3. This one is chapter 5. So the input signal is 2 unit step function, meaning that 2 volts. Okay. So when you take Laplace is R S equal to 2 over S. And this is the model. Okay. So it's the first order system. Okay. So we draw the diagram. Twenty S plus 20, where C over R is 20 S plus 20. Okay. But CS is equal to 2 over S multiplied by 20 S plus 20. Okay. Put back. It is 40 S plus 20. So we have to do partial fraction expansion to solve this problem. Okay. Okay. So you solve this A. How you solve it? A is equal to 40 over S plus S equal to 0, and B 40 over S is equal to minus 20. So this one is 2, and this one is minus. Okay. So when you insert inside, A is 2 over S, B is minus 2, S plus 20. So use the inverse Laplace. Okay. So C of t will become 2 minus 2 exponent minus 20t. Okay. So if you want to plot this, you have to use approximations. Okay, so when C0, 2 minus 2, 1, 0, C infinity 2 multiplied by 0 equal to 2. Okay, so it seems that the response is something like this. Okay, so this is 2 volt. Okay, and the response is first order system. Good. Okay, so from here we can calculate the time constant. Okay, so you can do like this. A S plus A. A is equal to 20. So time constant is 1 over A, 1 over 20, 0.05 seconds. Okay, rising time. Rising is equal to 2.2 divided by A. This formula is for first order system. And finally, the settling time is equal to 4 divided by A, 20, 0.2 seconds. Okay. Identify the steady state error of the system and plot the system response. So the steady state error is 0, okay, when t towards infinity. So no error. And this one is already plotted, okay, just now. Question B is this one. You're referring to figure 3B, okay? So 1 volt step input, and you are given a forward transfer function as shown, okay? System stability for the following case, okay? So first we write the open loop transfer function first. Question 3B, okay? Open loop transfer function, okay, which is k s plus 1 s plus 2. Okay, then find the closed loop transfer function, which is including the unity feedback. Find the characteristic equation, which is s cubic plus 3s square 2s plus k equal to 0. Okay. So the question asks system stability when k equal to 5, when k equal to 10. So just replace, substitute k is equal to 5 and see what happens. Plus 3s squared plus 2s plus 5. Okay, so now you have to use find the roots. Okay, or close loop poles. Okay, so I'm using MATLAB. So the closed loop poles S1, S2, okay, and 3 is minus 2.9 minus 0.05 plus minus J 1.31. Okay, so if you look here, the locations mapping for this kind of poles is located here and here. Okay, so from here, stability status is stable. Okay, due to all poles on the left half plane. Then we change the k, okay, and k equal to 10. So s cubic plus 3s squared plus 2s plus k equal to 0. Substitute 3s squared plus 10. Okay, k equal to 10. And see what happened. Find the roots using your calculator, or we call it as a closed loop poles. So the value will be 1 is 0.15 positive plus minus J 1.73. So when we plot on the S-plane, okay, so the poles located over here and over here. So you can see that system is not stable, okay, due to two poles located on the right half plane. Okay, so as simple as that. So based on the result obtained in one, explain how will the system behave if the gain change from k to higher values or infinity. So you can say that is the pole locations. Okay, on left half plane stable, on right half plane not stable. Question 3, C, where you are given RLC derive the transfer function of the system for voltage VC across the capacitor. So this one is a single loop. Second order system. Okay. Only single current flow inside the loop. So let's go on how to solve this. RLC. Okay. One hundred ohm, 1 millihenry, and how many farad? 100. Okay, so using Kirchhoff voltage law on single loop. Okay, so you will get VI IS R over LS over CS. And what is the output? The output is, we run for the voltage output VC. VC is the output. VI is the input. So VC is the output. So VCS. VCS. Okay. So this one we can change. It becomes okay. So VI, yes, CS, VCS multiplied by R RCS. Okay. So VC over VI 1 over plus 1 1 over LC S square RC over LC R over LS. Okay, so you insert all the value. This is the transfer function VC over VI. Then you are required to find undamped natural frequency and damping ratio. So compare. Okay. Tiga satu six two radian per second, and then 2 zeta omega n compare with 10 power of 6. Okay, so it is over 1 and it is over them. Okay, too slow, too slow. So over them meaning that the response is too slow. On vote, so the response is too slow. Okay. Question 4. So we have question 4 and question 5. So you have to choose either Q4 or Q5. So let us answer Q4 first. Okay. This is the block diagram. 4 over s plus 1, 5 over s plus 10, and 1 over s. Okay. Determine the location of the closed loop poles on the S-plane. So as usual, you find the open loop transfer function and then closed loop transfer function. Okay. Question 4. Open loop transfer function. Okay. Then closed loop transfer function. Then characteristic equation. S cubic plus 11 plus equal to 0. Okay. And find the roots. Or closed loop poles, which is minus 10 minus 0.394 plus minus G 1.34. Okay, so we map to the S-plane. Okay, so we already answered this one. It can be approximately a second order system. Explain why. The control system can be approximately as second order system. So we look here. Closed loop poles is minus 10, then minus 3, minus 0.394 plus minus J 1.34. Okay, so we found the ratio. Ratio. Okay. Minus 10 over the real part minus 0.39. So we find the ratio. 25, which is greater than 5. So second order is valid. Okay, guys, we continue on the step C. Okay. So we already answered part D. Now we move to part C, a unit step. Input is applied to the system. Determine the TS, TP, OS, and the steady state error. Okay. So let's go to the whiteboard. So this is Q4 part C. So use second order formula. Okay. Where Ts is equal to 4 divided by zeta omega n. So actually, zeta omega n is the real part of the complex conjugate pole. Okay, so if you look at the conjugate poles, is given by in previously minus 0.394 plus minus j 1.34. Okay, so guys, this one is real, this one is imaginary. So you took this value, put inside this formula, you take the modulus of 0.394. Okay, so you will get the value at 10.15 second. Okay, so no need to find zeta and omega n. No need. Okay, you just take the real part of the complex conjugate pole. The next one is TP. So TP also the same, where the formula is pi divided by omega d. So if you look at the complex conjugate poles, okay, which is minus 0.394, okay, plus minus j 1.34, which is this one actually is minus zeta omega n plus minus j omega d. So automatically the omega d value, okay, is here, which is on the imaginary part. Okay, so you use this value, put inside here. Okay, so you will get pi 1.34. Okay, which will give you 2.34 seconds. Okay, so remember omega d is omega n 1 minus zeta squared. So no need to find omega n and zeta. Okay, and then the next one is the overshoot percentage. Okay, so for overshoot percentage, Of course, you have the formula here, 1 over minus zeta square, okay, multiplied by 100%. But zeta, we don't know, right? We don't know the zeta, so in this case, you have to find the zeta. So since the complex conjugate pole is located over here, okay? So this one is minus 0.394 G 1.34. Okay, so you have to somehow find this angle, okay, theta, cos theta, cos theta is equal to zeta. So zeta is equal to cos, sorry, I will again, excuse me, theta is equal to inverse cos zeta. Okay, so we have to find this theta value. So this theta value actually is this length divided by this length. Okay, so theta is equal to 1 arctangent 1.34 divided by 0.394. Okay, so this one will give you 0.281. Okay, sorry, this angle okay, you have to find this angle first. Okay, find this angle. Okay, and then straight away plug in into the zeta, which is cos theta. So cos arctangent 1.34 divided by 0.314, which will give you 0.281. Okay, and then from there you can calculate the overshoot, which is exponent 1 minus zeta square percent, which is 39.8%. Okay, so for steady state error, ESS is 1 over 1 plus Kp, okay, due to step input. So Kp is position constant, okay, error constant, and Kp is equal to, we need s to 0 Ks, and K in this case what is the K value here? Let me look here. Okay, this one. Okay, this one. Okay, 20 S plus 1, S plus 10. Okay, 20 S plus 1, S plus 10. S plus 1, S plus 10. Okay, so we just insert the value. Okay, insert the value, which is 20, 0, multiplied by 1, multiplied by 10. So it will give you infinity. The steady state error is 1 over 1 plus Kp, 1 over 1 plus infinity. So this one will give you 0. Okay, the steady state error will be 0. Then sketch the expected output response from the information obtained. Okay, since it is zeta is equal to 0.281, it is under dam. Okay, under dam response. So simply 1 volt input. Okay, output time. So steady state error 0. So it will be like this. Okay, so this is the output. Okay, and next, determine the stability of the closed loop system. So the closed loop poles, okay, poles is minus 10 minus 0.394 plus minus J 1.34. So system stable. Okay, due to all located at the left of plane. Okay, if a controller is added to the system as shown in figure Q for B, determine the range of gain K for this system to be stable. So what you do is you find the open loop transfer function first, and then you find the closed loop transfer function, and then you find the characteristic equations, and then go to the Ruth Lewis table. Okay, so what I will do is I write the open loop transfer function. Okay, which is K S plus 5, 20, S plus 1 plus 10. Okay, and then find the closed loop transfer function. Okay, 20K S plus 5. and find the characteristic equation. Go to 0. Okay. And simplify. Characteristic equation. Okay, which is s cubic 11 s square plus 10 plus 20k s plus 100k go to 0. Then plug in the coefficient values in the root width table. Okay, so we open the root width table. Which is 1, 11, K, 100K, 0, 0. So this one will be 110 plus 120. Okay, 0. This one will be 110 plus 120K over 11. Okay. Sorry, this one is wrong. Okay. This one is supposed to be 100K, 100K. Okay. So identify the first column. So this one is the first column. Okay. The theory said range of K for stability. Okay. First column must greater than 0. So in this case, this one is greater than 0. Greater than 0. Okay. So we took this one, 110 plus 120K divided by 11 greater than 0. 110 plus 120K greater than 0. Okay. 120K minus 110. Okay. So K is minus 11 over 12. And the second one is 100K greater than 0. K greater than 0. So the range of K for stability is K greater than 0. Okay. So I answer these questions. And question number 5, the last one. Okay. Where you are given inner loop and unity feedback, okay, of a hydraulic actuator system. Unit step input. Okay. So determine the closed loop transfer function. So you have to derive, okay, this one. So this one is feedback, cascaded, 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 and then find the feedback 1, feedback 2. Okay. So what I will do is something like this. Okay. Question 5a. Okay, find the closed loop transfer function. One plus 1.2. 1.2 s plus 1. Okay, simplify. So you get 0.5k s square okay. So this is the closed loop transfer function. Then find the omega n and the value of k to produce a damping ratio 0.5. Okay. Right. So what you should do is 2 zeta omega n 0.8. Okay, so zeta 0.5. That's why your omega n is equal to 2.5 radian per second. And then omega n square is equal to 1.2 plus 0.4 k divided by 0.8. Okay, which is equal to 2.5 square. That's why your k is 9.5. Okay. Find the steady state error of the system to a unit step input by using the value of k obtained in part B. So as I told you before, we find the GS. Okay. Find the GS. So in this case, okay, let me derive the open loop transfer function first. Derive open loop transfer function, which is k multiplied by 2 over s plus 1. K multiplied by 2 over s plus 1. This one is 0.2. Okay, 0.2, 0.8 s plus 0.2 over 0.8 s plus 1 plus 1 plus 0.2. So this is the inner loop simplified. Okay. So now ds will become 0.4k s plus 1, 0.8 s plus 1.2. Okay. So k is 9.5. So gs equal to 9.5 multiply 0.4k, 0.4 s plus 1, 0.8 s 1.2. Okay, so this is your gs with k. So ess is 1 over 1 plus kp, step input, kp position error constant. Okay, so find the kp, which is limit s to 0 gs. Okay, so kp is equal to 9.5 multiply 0.4 divide by 1 multiply 1.2. So how much? Use your calculator. 9.5 multiply 0.4 divide by 1.2 is 3.2. 3.16. Okay. So use this KP, insert inside your formula. Divide 0.24. Okay, so the steady state error now is become 0.24. Okay, so for certain usage of the system, it is modified by adding a subsystem into the basic configuration as shown in figure Q5B. So you add this instead of K here, change to here. You add another one. Okay, right? So B, okay, this one. Okay, so find the open loop transfer function first, ds. Okay, forward. After that, find the closed loop transfer function. Okay, which is ts. Then find the characteristic equations. Right. So what I will do is we simplify the forward path. Okay. where this one is x squared minus 0.4 over okay. Find the closed loop transfer function. So you will get 0.4k plus 2 0.8 plus 0.4k okay. So characteristic equation is 0.8 k square plus 2 minus 0.8 k s plus 1.2 plus 0.8 k equal to 0. Okay, so plug in the coefficient value to the RH table. Okay, which is s square, s1, and s0. So you will get 0.8 plus 0.4 k, 2 minus 0.8 k, 1.2. So for stability, first column greater than 0, which is this one. Okay. So 0.8 plus 0.4k greater than 0, greater than minus 2, equation 1. 2 minus 0.8k greater than 0, and negative 0.8k greater than minus 2, and k less than 2.5, equation 2. 1.2 plus 0.8k greater than 0. So k greater than minus 1.5. Okay. Also, k greater than 0, equation 4. So you have 4 range over here. Okay. Then you accumulate, then you simplify. So the range of k will be 0, k less than 2.5. So this is the final range of the stability. And the final one is if the system part B is marginal stable, determine the new frequency of oscillation omega n. So I repeat again, okay, range of k for stability is, as we derived just now, is 0, k, 2.5. Okay. So in the class, I already told if k between 0 and 2.5, example, k equal to 1, system stable. Okay. If k is equal to 3, system not stable. But if K is equal to 2.5, is a marginal stable. This is very important, okay? Because this is the keyword. You use the value of K, okay, to solve the omega n values, okay? In this case, you will do is you go to the Roth-Lewis equations. Okay, you choose polynomial. This one. Okay, you choose this polynomial. Okay, choose this polynomial. Okay, which is PS 0.8 plus 0.4K S square plus 1.2 plus 0.8K. Okay, for K equal to 2.5, this is marginal. Okay, so PS equal to 1.8 S square plus 3.2 equal to 0. Then S will be plus minus J 4 over 3. And this is plus minus J omega. Okay, so the omega will be 4 over 3 radian per second. Oscillation frequency. Okay, which will give you something like this. The response, okay, is a marginal and oscillate towards infinity. Okay, guys, that's all for today. Thank you very much for your attention. All the best to you. Thank you very much.